I'm going to make an argument that will sound pessimistic, maybe even depressing, but I think it's probably correct based on what we know about physics, biology, and the universe. Intelligent life is unlikely, extraordinarily, improbably, astonishingly unlikely. We might be alone in the galaxy. We might even be alone in the observable universe. And the silence we hear when we listen for alien signals, the deafening cosmic silence, might not be because we're looking in the wrong way or listening on wrong frequencies. It might be because there's simply nobody out there. I've spent my career thinking about the universe on the largest and smallest scales. And the more I learn, the more I appreciate just how special, how contingent, how fragile the emergence of intelligent life really is. Let me start with the Fermi Paradox, because that's where this whole discussion begins. In 1950, the physicist Enrico Fermi was having lunch with colleagues at Los Alamos National Laboratory. They were discussing flying saucers and whether extraterrestrial civilizations might exist. And Fermi asked a simple question: where is everybody? His point was this: the Milky Way galaxy is about 13 billion years old. It contains somewhere between 100 billion and 400 billion stars. Many of those stars have planets. We know this now from exoplanet surveys like Kepler and TESS. If even a tiny fraction of those planets developed intelligent life, and if even a small fraction of those civilizations developed space travel, the galaxy should be teeming with evidence of alien civilizations. They should have colonized the galaxy by now. They should have sent out probes. We should see their megastructures, their radio signals, their waste heat. We should see something, but we don't. We see nothing. The sky is silent. No signals, no visits, no artifacts, nothing. This is the Fermi Paradox. If intelligent life should be common, why do we see no evidence of it? There are many proposed solutions to this paradox, hundreds of them actually, but I want to focus on one particular category of solutions, the one I find most compelling. Intelligent life is rare, vanishingly rare, maybe unique. Now, this goes against the Kaepernick principle, the idea that Earth is not special, that we're a typical planet around a typical star. And for a long time, I believed in the Kaepernick principle. I thought intelligent life must be common. The universe is so vast, the numbers so large, that intelligence must have arisen countless times. But the more I've learned, the more I've changed my mind. Let me walk you through the Drake equation, because it's a useful framework for thinking about this problem. In 1961, the astronomer Frank Drake proposed an equation to estimate the number of detectable civilizations in our galaxy. It looks like this. N equals RA times F sub P times N sub E times F sub L times F sub I times FC times L. Let me break that down. N is the number of civilizations we might detect. R star is the rate of star formation. F sub P is the fraction of stars with planets. N sub E is the number of planets per star that could support life. F sub L is the fraction where life actually develops. F sub E is the fraction where intelligent life emerges. FUBC is the fraction that developed detectable technology. And L is how long they broadcast. Now let's plug in some numbers. R star, the star formation rate is about 1 to 3 stars per year. We know that pretty well. F sub, the fraction of stars with planets, is close to 1. Almost every star has planets. Kepler has shown us that. N sub A, the number of habitable planets per star, is harder, but estimates range from 0.1 to 0.4, so roughly 10 to 40% of stars might have a planet in the habitable zone. So far, the numbers look good. There should be billions of potentially habitable planets in our galaxy, but now we get to the really uncertain terms. F sub, fraction of habitable planets where life actually develops. We have one data point, Earth. Life arose here about 3.8 billion years ago, relatively quickly after the planet formed. Does that mean life arises easily, or did we get lucky? We don't know. Estimates for F sub range from close to 1 down to 10 to the minus 10 or lower, 100 orders of magnitude of uncertainty. Then there's F sub, the fraction of life-bearing planets where intelligent life emerges. And this is where I think the real problem is. On Earth, life has existed for 3.8 billion years. For most of that time, about 3 billion years, life was nothing but single-celled organisms, bacteria, and archaea. No multicellular life, no complexity, just single cells doing their thing. Then about 600 million years ago, something extraordinary happened. The Cambrian Explosion. Suddenly, geologically speaking, multicellular life appeared. Animals, complex body plans, eyes, nervous systems, predator-prey relationships. The diversity of life exploded. Why did it take 3 billion years for this to happen? We don't really know. But it suggests that the transition from single-celled life to complex multicellular life is not easy. It's not inevitable. It requires special conditions that may be rare. Let me dig deeper into this because the timeline is crucial. For the first 2 billion years of life on Earth, there wasn't even any oxygen in the atmosphere, zero. The atmosphere was mostly nitrogen, carbon dioxide, and methane. The oceans were filled with single-celled organisms doing anaerobic metabolism. Then around 2.4 billion years ago, something called the Great Oxidation Event occurred. Cyanobacteria had been producing oxygen as a waste product for hundreds of millions of years. And at first, this oxygen was absorbed by iron dissolved in the oceans, forming rust that settled to the ocean floor. But eventually, all the iron was oxidized and the oxygen started accumulating in the atmosphere. This was catastrophic for most life at the time. Oxygen was toxic to the anaerobic organisms that dominated Earth. It was probably the first great mass extinction, but it also created an opportunity. Oxygen enables aerobic respiration, which is far more efficient than anaerobic metabolism. An aerobic organism can extract about 18 times more energy from glucose than an anaerobic one. This extra energy is what makes complex multicellular life possible. But even after oxygen appeared, it took another 1.8 billion years for complex life to emerge. Why? One problem was that oxygen levels fluctuated wildly. There was a period called the Boring Billion from about 1.8 billion to 0.8 billion years ago where oxygen levels were stuck at maybe 1 to 10% of modern levels, too low to support complex animals. It wasn't until around 800 million years ago that oxygen levels started rising again. And even then, there was the snowball Earth period between about 720 and 635 million years ago when the entire planet froze over, possibly multiple times. Ice covered the oceans from pole to equator. Life barely survived. The Cambrian Explosion happened only after all of these crises were resolved, after oxygen stabilized, after the planet thawed, after conditions became just right. And here's what disturbs me. There's no reason to think this sequence is inevitable. Oxygen production, the Great Oxidation Event, surviving the snowball Earth. These were contingent events. They could have failed to happen. Earth could have remained a planet of bacteria forever. And then even after complex life emerged, it took another 600 million years for intelligent life, us, to appear. Think about that timeline. Out of 4.5 billion years of Earth's history, complex life has only existed for the last 600 million years. About 13% of the time. And intelligent technological life has only existed for a few tens of thousands of years, about 0.01% of Earth's history. For 99.999% of Earth's existence, there was no intelligence, just bacteria living and dying, but never thinking, never wondering, never knowing. Now, let me talk about the evolution of intelligence itself, because this is another massive bottleneck. Intelligence is not an inevitable outcome of evolution. It's not even obviously advantageous in most ecological niches. Consider dinosaurs. They dominated Earth for about 165 million years, far longer than mammals have existed. And in all that time, not one dinosaur species developed anything approaching human-level intelligence. Some dinosaurs had large brains, some were social, some may have used tools in rudimentary ways, but none of them built cities, created language, or developed technology. Why not? Because intelligence is expensive. A human brain uses about 20% of the body's energy budget, despite being only 2% of body mass. That's an enormous metabolic cost. And for most of evolutionary history, that cost didn't pay off. Being a successful predator doesn't require intelligence. Sharks have been extremely successful for 450 million years with relatively small brains. Being a successful herbivore doesn't require intelligence. Grass has conquered huge swaths of the planet without a single neuron. Intelligence only becomes advantageous in very specific ecological niches, niches that reward problem-solving, tool use, social cooperation, and long-term planning. On Earth, that niche was occupied by early hominids in Africa. savanna-dwelling primates who faced variable environments, needed to hunt cooperatively, and benefited from making tools and sharing knowledge. But that's one lineage out of millions. Only one our lineage developed high intelligence. Crows are intelligent, octopuses are intelligent, dolphins are intelligent. But none of them developed technology, none of them created civilization. The biologist Ernst Mayr argued that this shows intelligence is not an evolutionary inevitability. Most species do perfectly fine without it. His conclusion was that F Subi is very small, maybe 10 to the minus 9 or smaller. If that's right, then even if every habitable planet develops life, intelligent life is still extraordinarily rare. Now, let me tell you about some recent work that makes the picture even blearer. In 2024, two planetary scientists, Robert Stern and Tusgeria, published a paper proposing that the Drake equation is missing two crucial terms. They argue that plate tectonics and the presence of both continents and oceans are essential for intelligent life to develop. Plate tectonics does several important things. It recycles carbon between the atmosphere and the Earth's interior, regulating climate over geological timescales. It creates diverse environments that drive evolution. It may have played a crucial role in the Cambrian Explosion by increasing oxygen levels. And crucially, plate tectonics requires specific conditions. The planet needs to be the right size, it needs liquid water, it probably needs a large moon. Stern and Geria estimate that the fraction of habitable planets with significant continents, oceans, and long-lived plate tectonics is somewhere between 0.003 and 0.02. That's tiny. Even at the high end, that's only 2 planets out of every 1,000 habitable planets. When you multiply this into the Drake equation, the number of expected civilizations drops dramatically. You get numbers close to 0, maybe 1, maybe less than 1, us alone. But let me add another layer to this problem. Even if life exists elsewhere, detecting it is extraordinarily difficult. We've discovered over 5,000 exoplanets. We can measure their masses, their orbits, sometimes their atmospheric composition. In principle, we could detect biosignatures, gases that indicate life. The most obvious would be oxygen combined with methane. On Earth, these coexist in chemical disequilibrium because life constantly produces them. But here's the problem. We haven't detected these signatures on any exoplanet yet. The James Webb Space Telescope has the capability to detect biosignatures on small rocky exoplanets. We're finally reaching the point where we could detect life if it exists on nearby worlds, but we haven't, not yet. And the longer we look without finding anything, the more the silence becomes meaningful. Even if we detected biosignatures, that would tell us life exists, but it wouldn't tell us intelligent life exists. For that, we need technosignatures, evidence of technology. And here the challenge becomes even more daunting. On Earth, human civilization has been producing detectable radio signals for less than 100 years. Our radio bubble has a radius of only about 100 light years. The Milky Way is 100,000 light years across. Our radio bubble covers about 1/1,000,000th of the galaxy's volume. If another civilization exists and they're at our technological level and they started broadcasting at the same time we did, the chances of our radio bubbles overlapping are minuscule. And that's assuming civilizations continue broadcasting. We're already shifting away from powerful broadcast radio. In another 100 years, we might be undetectable. There's also the problem of what frequency to listen on. The electromagnetic spectrum is vast. We've searched a tiny fraction of it at a tiny fraction of the sky for a tiny fraction of the time. It's like scooping a cup of water from the ocean and concluding there are no fish. But despite these challenges, I think the null result is significant. We've been looking for over 60 years. If intelligent life were common, we should have found something by now. Now, you might object. You might say, I'm making Earth-centric assumptions. Maybe life doesn't need plate tectonics. Maybe silicon-based life in ammonia oceans could develop intelligence just fine. And you'd be right to push back. We only have one example of life, Earth life. Extrapolating from one data point is dangerous, but we have to work with what we know. And what we know is that on Earth, intelligence required billions of years of evolution, specific geological conditions, and a lot of luck. Let me talk about the Great Filter because it's relevant here. The Great Filter is a concept proposed by Robin Hanson. The idea is that somewhere between the formation of a planet and the development of a galaxy-spanning civilization, there's a barrier that prevents most attempts at life from succeeding. The question is, where is the filter? Is it behind us or ahead of us? If the filter is behind us, if the hard step is going from non-life to life or from simple life to complex life, then we've already passed it. We're past the hard part and our future might be secure. But if the filter is ahead of us, if the hard step is surviving long enough to colonize the galaxy, then we're in trouble. It means most civilizations destroy themselves before they can expand. Nuclear war, climate change, artificial intelligence gone wrong, pandemics. There are many ways a technological civilization could end. And here's what's disturbing. We have no evidence of civilizations that made it past the filter. The sky is silent. That suggests that either the filter is behind us, meaning intelligent life is rare, or the filter is ahead of us, meaning we're doomed. I'm hoping it's the former. Now let me address the argument from large numbers. I hear this all the time. The universe is so big. There are so many stars. Even if the odds are tiny, there should still be lots of civilizations. I used to find this compelling, but I don't anymore. Even if the universe is vast, the probabilities can be even vaster. If the probability of intelligent life arising on any given habitable planet is 10 to the minus 21, you'd expect fewer than one civilization in the entire observable universe. We have no way of knowing if 10 to the minus 21 is too pessimistic. It could be 10 to the minus 50. The point is, large numbers don't help if the probabilities are small enough. Yes, there are billions of planets, but if the odds are tiny enough, those billions don't matter. Now, here's where this connects to my own work on the string landscape and the anthropic principle. In the multiverse picture, there are an incomprehensibly large number of different universes. Most are sterile, dead, unsuitable for life because the constants of nature are wrong. We exist in one of the rare universes where conditions allow for life. That's observer selection. We couldn't exist in any other kind of universe. But here's the key question. Within our particular universe, how common is life? The multiverse explains why our universe has the right laws, but it doesn't guarantee that intelligent life is common within our universe. It's possible that even in a life-permitting universe, the actual emergence of intelligent life is so improbable that it happens only once. The anthropic principle explains why we exist, but it doesn't explain why there should be lots of us. The weak version just says we exist in a universe compatible with our existence. The strong version says the universe must produce observers. I believe in the weak version. And if I'm right, then the fact that we exist doesn't imply that intelligent life is common. It just implies that it happened at least once. Think about the lottery analogy. If you win the lottery, that doesn't mean lots of other people won too. It just means someone won. You. We won the cosmic lottery. We exist in a life-permitting universe on a planet with the right geology, the right history, the right evolutionary contingencies. That doesn't mean there are lots of other winners. It might just mean we got lucky. The observer selection effect might be masking our uniqueness. If intelligent life is incredibly rare, maybe unique, we would still expect to find ourselves in exactly the situation we observe, a habitable planet in a life-pitting universe surrounded by a vast cosmos that appears empty because that's the only kind of place where observers can exist. The universe could contain 1 million civilizations or just one. From our perspective, we couldn't tell the difference. This is deeply unsettling. It means the data we have, our own existence, the silence of the cosmos, is compatible with both possibilities. We can't distinguish between them observationally, at least not yet. All we can do is make estimates based on what we know about biology, geology, and the history of life on Earth. And those estimates suggest that intelligent life is rare. Now, there's maybe one more thing I want to talk about. The temporal aspect. The universe is about 13.88 billion years old. Our sun formed about 4.6 billion years ago. We're relatively early. There could have been civilizations that arose billions of years ago. And if they developed space travel, they've had billions of years to colonize the galaxy. The galaxy should be completely filled with their descendants. But it's not. This is sometimes called the Hart-Tipler argument. The absence of aliens on Earth proves that no extraterrestrial civilizations exist because if they existed, they would have colonized the galaxy by now, including Earth. There are counter-arguments. Maybe civilizations don't colonize. Maybe they have ethical prohibitions. Maybe they self-destruct. Maybe we're in a zoo. These are all possible, but they feel like ad hoc excuses. The simplest explanation is that we're alone. I want to talk about the rare Earth hypothesis because it encapsulates many of these arguments proposed by Peter Ward and Donald Brownlee. It argues that complex life is rare because it depends on a long chain of unlikely events and conditions. The right kind of galaxy, the right kind of star, the right position, the right planetary system, the right planet with plate tectonics, a magnetic field, a large moon, the right amount of water. Each of these conditions might be rare. Multiplied together, they become vanishingly rare. The rare Earth hypothesis doesn't say life itself is rare. Microbial life might be common, but complex animal-like life, intelligent life, that's the rare part. And the evidence from Earth supports this. For billions of years, Earth had only microbes. Complex life appeared late and only after a series of improbable events. If you could rewind the tape of life and play it again, would intelligence emerge again? Probably not. Stephen Jay Gould made this argument in his book, Wonderful Life. He argued that if you replay the tape of evolution, you get a completely different outcome each time. Contingency dominates. The Cambrian Explosion produced a vast array of body plans, most of which went extinct. The ones that survived were not inevitable. They were lucky. This is the deepest lesson from paleontology. Evolution is not a ladder leading inevitably to humans. It's a branching bush with millions of twigs. Most paths lead nowhere. Ours led to intelligence, but it could easily have led elsewhere. But I want to end on a slightly different note. Even if we're alone, even if the universe is empty, that doesn't make us less significant. In fact, it makes us more significant. We are the universe's way of knowing itself. We are the consciousness that has emerged from stardust to contemplate the stars. If we are alone, then we have a responsibility. We are the only ones who can appreciate the beauty of a galaxy. That thought should sober us. It should make us more careful, more thoughtful, more humble. The silence of the cosmos is not a sign of our insignificance. It's a sign of our rarity, and rarity is a form of value. The rarest things are the most precious. We are precious. Earth is precious. Life is precious. And intelligence, fragile and improbable as it is the most precious thing of all. So let's not waste it. Let's not destroy ourselves. Let's grow up as a species, solve our problems, and go out into the universe. Not to conquer, but to explore. Not to exploit, but to appreciate. Not to find others, but to become the others that someone else might one day find. Because even if we're alone now, we don't have to be alone forever. We can spread life to other worlds. We can see the galaxy with consciousness. That's our potential. That's our destiny if we choose it. And that's what I think about when I look up at the night sky and see the stars and hear the silence. I don't hear emptiness. I hear possibility. I hear a challenge. Are we up to it? I don't know, but I hope so. I really hope so.